Good afternoon and welcome to our webinar. My name is Rusty Giudice. I'm the president and founder of Advanced FRP Systems. Today we will be discussing composite repairs for pipe type cables, specifically talking about how we can help you increase the efficiency of maintaining these critical assets, as well as enhancing the overall reliability of your system. So once again, thanks for joining us. The agenda for today's presentation, we're going to start with a little background discussing pipe type cables in general. We're going to look at some traditional welded repairs versus composite repairs for these assets. We're going to talk about some custom composite repairs for pipe type cables. Then I'm going to show you how this is a truly permanent solution with long-term reliability. And finally, we're going to have a QA section. To facilitate the presentation, we'll be taking all of our questions at the end of the webinar during the Q&A session. Please type in any questions as we go, and we can compile the list of questions, and I'll answer them live at the end of the presentation. So before we dive into composite repairs, here's a quick background on pipe type cables. For those of you who aren't familiar with pipe type cables, there's a few different types of pipe type cables. They're generally speaking high voltage underground power transmission piping systems. You'll see a schematic on the right here for a high pressure fluid filled system. High pressure fluid filled pipe type cables are some of the most common cable systems that we see in operation right now. Many of these systems, they're aging, they're over 50 years old. When they've been buried for over 50 years, the protective coating that's protecting the external shell of the pipe type cable is nearing or past the end of its service life. Once coatings are past the end of their service life, that's going to lead to corrosion of the steel host pipe. Corrosion of the steel host pipe will eventually lead to dielectric fluid leaks. Dielectric fluid leaks can have severe financial, environmental, and service implications. One particular client has given us an estimate of about $200,000 to fix a leak in their dielectric fluid. So clearly we want to make sure that doesn't happen. There's some traditional repair options that have been used, an externally welded barrel or external welded repair. We're going to kind of go through what that would look like, an external welded repair on a pipe type cable system. So the first step, locating the leak. Next, these are almost always buried piping systems, so you'll have to excavate to unearth the pipe itself for the repair. Prior to doing any sort of repairs, you're going to have to remove the external corrosion barrier, a coating or a tape coat or whatever it might be. If you want to repair more than just the exact spot of the leak, you can do a corrosion assessment and see where else on that area you've unearthed may be experiencing corrosion. A clamp can be installed to stop the active leak from leaking. Next, an external barrel is welded onto the pipe type cable. After that barrel is welded on, it's pressure tested to ensure there's no porosity in the welds or any leaks. And finally, a new corrosion protection barrier is installed, and then the pipes can be buried. So it sounds simple enough, but there are some issues with our current approach to repairing pipe type cables. The issues with this current approach, the biggest thing, we're really relying on the cathodic protection of these systems because so many of these systems are operating with coatings past their service life. Cathodic protection is great as a secondary corrosion barrier, but as more and more failures happen on your protective coating, it's going to overwhelm the cathodic protection and you're going to get corrosion regardless. A lot of the current practices, what I just described, it's a very reactive practice of repair. There's no real monitoring of corrosion on these systems. It's not practical to monitor internally, and monitoring externally requires digging them up. So we basically just repair active leaks or extremely severe corrosion. Also, external weld repairs, like I showed you, those barrels, they're not real practical for large repair areas. For a spot repair, they're a reasonable solution, but if you want to repair 50 feet of pipe, it's going to be a lot of welded barrels. So, I'm telling you that it's a reactive solution. Are there better solutions out there? And I think the answer is yes, and that's what we're going to talk about here. Um, Composite repairs for piping systems are something that have been around for a while now, and they're pretty popular in other industries, in power generation, um, including nuclear power generation, even safety-related piping in nuclear generation. They use carbon fiber composite repairs for critical piping systems. In the oil and gas industry, they're using composite and carbon fiber repairs for pipes, and in water and wastewater. So it is a pretty extensively used process for repairing pipe externals. Why are we talking about carbon fiber as a solution? So let's dig into that. First, the tensile strength of carbon fiber. It's a really strong material. You can see it's about 3 times the tensile strength of carbon steel. The density is also very low. So if you're doing repairs on, bridge crossings and other suspended lines, the weight of a carbon fiber repair is significantly lower than that of a barrel repair. Finally, the thermal conductivity. Carbon fiber is a non-metallic, so it is lower in thermal conductivity than a metal like carbon steel. But for reference, a general corrosion-resistant coating is going to be closer to 0.2 watts per meter Kelvin. Carbon fiber is at 8 watts per meter Kelvin and is actually extremely thermally conductive for a non-metallic. This is crucial for underground feeder lines because they rely on the dissipation of heat. So carbon fiber will not inhibit the dissipation of heat through the pipe wall. So what is a carbon fiber composite? Let's kind of dive into that. The basics of it, we take carbon fiber filaments, they're woven into a pliable fabric that you can see here. This fabric is saturated with a 2-part epoxy resin, and then it's wrapped around the OD of the pipe. The resin cures through a chemical cross-linking mechanism, and it creates a hard, strong composite that fits perfectly around the outside of the pipe. You can see a repair in action right here. The reason that this repair is very different than just a coating system is the carbon fiber is fully structural. It creates a secondary pressure boundary capable of containing up to 1,000 psi of internal pressure. It's non-metallic, so it doesn't corrode as well. So there's no coating system that can fail. This is going to last 50 plus years in the ground without having any corrosion. And these composite repairs are done with these feeders still in service. All right, let's talk about a composite repair and exactly what it would look like. So in the same scenario with a leaking feeder line, the first 2 steps are the same. We locate the leak and we excavate. After that, we actually don't have to remove the existing coating. We just put a clamp on it or use another technique to stop the leak. After the leak is stopped, we will identify something called an adhesion zone, and we'll grip blast around on either side of the leak where the adhesion zone is, and that will allow us to wrap this pipe. Finally, we'll install the composite repair system and we'll apply a top coat. So we looked at 2 scenarios, one using external welds and the other using a composite, and they're fairly similar. Some distinct differences and some advantages of the composite, but I want to highlight one really important point of the composite repairs. It's this adhesion zone technology. I touched on it on the last slide. What this means is it's really efficient to do large-scale repairs with composites. The exact opposite of welded repairs, where it's really efficient to do a small welded repair, but large repairs are difficult. We can wrap up to 50 linear feet of cable in a single shift without fully removing the external coating, without any welding, and without performing a comprehensive corrosion assessment. The key to it is, like I said, the adhesion zone technology. We can encapsulate 100 feet of feeder lines, and we only remove the coating and grip blast 3 feet on either end. So 94% of that surface does not have any surface preparation outside of just cleaning off some dust, dirt, and debris and smoothing it off. So this is cutting down over 90% of your surface prep. It's also crucial because a lot of these feeders have been in the ground for, like I said, 20 to 50 years. They may have an asbestos containing coating on them. They may have a lead coating on them or a PCB containing coating. Any of these coatings will greatly increase the cost and the difficulty of removing the external coating. So by not having to remove it, it's a huge asset. Plus, when you do a composite repair, you're reinforcing 100% of the cable that you unearth. So if you dig up 100 feet, you can reinforce 100 feet. If you dig up 1,000 feet, you can easily reinforce 1,000 feet, giving yourself a minimum of 50-year life extension. And this is all done with these transmission lines in service. So I've told you a little bit about composite repairs. Let me tell you about composite repairs that are specific to pipe type cables. So in order to ensure that the composite repairs wouldn't have any effect on these underground power transmission lines, we had to do a lot of testing. We did thermal conductivity testing of the composite itself to be able to model how heat would flow through it. And then a full heat transfer study was performed on a underground power line with a carbon fiber composite on it. We wanted to ensure that we were going to allow heat to dissipate through the system, even with large scale composite repairs. We also wanted to do something called a freeze test. Some of our clients used liquid nitrogen to freeze the dielectric fluid inside of these lines in order to do internal repairs of the conductors. So we wanted to ensure that they would still be able to freeze the dielectric fluid, and that freezing with liquid nitrogen at over or below minus 300 degrees Fahrenheit, we wanted to ensure that thermal shock wouldn't damage the pressure capacity of our carbon fiber repair. So we did those thermal tests. We also do a lot of pressure testing. We had to complete a comprehensive ASME PCC2 Table 1 test protocol to verify that we could comply with this specification for non-metallic repairs. We also did a lot of live hydrostatic test. So we're not going to test this when it's in the ground. So we basically had to test every scenario we were going to run into. When doing large sections of pipe type cables, there's pipe supports, temporary pipe supports in place. We ran into splice joints or hi-hats, existing barrels from previous repairs. Plus, defects are going to happen in composite repairs when you're doing long sections. So we fully pressure tested all these different potential issues that we were going to run into in the field, all up to 1,000 PSI with a through wall failure in the hose pipe. And that's crucial that we had a through wall failure in the hose pipe. So the carbon fiber was taking 100% of the load in all those scenarios. I think I can say confidently that Advanced FRP is the only company to comply with all these requirements specific to pipe type cables. We've done a lot of work in the field as well. So you can see starting in 2016, we did some pilot work. We've done work in tunnel systems. We've done high pressure gas filled lines that were at bridge crossings. We've also done spot repairs of horizontal directionally drilled piping systems. We've reinforced lead sheath feeders, and we've done work inside of manholes with huge splice joints and other things on the pipes. So I'm going to kind of talk you through why we have shown that this is a truly permanent solution for repairs on pipe type cables. Advanced FRP has reinforced more than 12,000 linear feet of pipe type cables with our carbon fiber composite system. And we've seen a lot in that process, and we've been able to ensure that our system was not only compatible with the things that we ran into, but would provide that same 50-year service life in all these different scenarios. So the first thing we ran into, an underground high pressure fluid filled pipe type cable that had stray current in that area that was greatly accelerating the corrosion rate. This complicated our repair in two ways. One, there was dozens of pre-installed barrels or externally welded repairs. So it wasn't a straight pipe anymore. And two, we had to look at how that stray current was going to affect the carbon fiber composite. We were able to fully reinforce this section of feeder, over 10,000 linear feet of pipe with a 6-layer composite carbon fiber system. We showed that it was not affected by the stray current and that it would completely eliminate the corrosion of the host pipe, as well as providing a secondary pressure boundary. We also ran into some unique issues with high pressure gas filled pipe type cable systems. So certain utilities at bridge crossings switch from dielectric fluid to nitrogen gas. So on these feeders, they were a gas filled feeder system, and there was numerous leaks on this particular feeder system we reinforced. Um, Not only were there numerous leaks, but the pipe supports themselves were aging in pretty bad shape. So the amount of weight that we added to these feeders was critical. Um, with carbon fiber, the low density that I showed you, we were able to add a minimal amount of weight while providing a completely leak-free system, even with numerous through-wall failures. And this was all done on vertical piping and piping with irregular elbows. So we had no issues with the vertical piping, um, and no issues working on scaffolding or with the elbows. Another issue we saw in the field was on something called a horizontal directionally drilled piping. Sometimes when you can't dig a big trench in a system in an area for whatever reason, this is another technique where you basically drill or bore a hole in the area and you pull the pipe through. This particular utility had used a traditional girth weld protection system. So, they had thought about the fact that their girth welds could be damaged during this process. Unfortunately, for whatever reason, the system that they chose wasn't up to the task, and they have leaks at several girth welds within their horizontal directionally drilled section of pipe. So because we knew these were isolated leaks, we were able to do spot repairs. The key on this repair, doing spot repairs, these weren't particularly old feeder lines. We needed to tie back into the existing coating and not leave the opportunity for spot corrosion at the end of the repairs. So we were able to design a system that could be tied back into the existing coating. Um, we were able to spark test it to verify that there was no gaps or voids in our coating system, despite the fact that we used a carbon fiber composite. We also ran into an issue where a lead sheath feeder was leaking. These are lower pressure feeder technologies, but the lead sheath is much softer than a standard carbon steel pipe. So grit blasting was not feasible. So we validated an alternate adhesion or an alternate surface preparation method for the adhesion zones on this lead sheath feeder. And we were able to design a custom solution that protected the lead sheath feeder, prevented any leaks, adhered to the surface with over 2000 psi of adhesion. And also we needed to make sure we didn't create a stress point at the end of the carbon fiber. So we had to taper that carbon fiber down so that there wasn't a stiff point right at the end. And the last installation spotlight was for a manhole. We've done several manholes with carbon fiber composite. A particular utility was experiencing corrosion in their manholes. Everyone has manholes in their feeder systems. Manholes are particularly difficult locations because it's an intermittent immersion condition. So you can get salt water runoff from the road, high humidity levels, all sorts of detrimental things to the steel that's going to be in those conditions. So we see varying degrees of degradation in manholes, and you often can't tell how bad your manhole is until you completely remove the existing coating and do an assessment. So what we did was we developed a versatile repair option. So if you remove all the coating and there's significant corrosion, we can fully structurally reinforce the manhole feeder with carbon fiber. If there's less significant corrosion, spot structural reinforcement can be installed, or you can do a partial structural reinforcement where you're just enhancing the strength of that steel pipe. Finally, you could just do a better protective coating system, a newer coating system, to allow you to get a long-term life extension. So to quickly summarize what we talked about, I know there's a lot of points in this system, in this presentation that we touched on, but if there's just four things that you take home from this presentation, this is kind of what it is. One, reactive maintenance of pipe type cables are going to result in more leaks as these systems age. So no matter what you do, if you're only fixing leaks that form and you have a coating system that's past the end of its service life, you're going to get more and more and more corrosion. In year one, you might have one leak. By year 10, you could have 50 leaks in your system if you don't start to take advantage or start to take advantage of a more proactive system. Second, standard doesn't mean good. There's a lot of industry standard stuff that we do that people have just done. Um, it doesn't always last the test of time. We've seen many areas where the standard repair did not work, and alternate, better repair systems are certainly the way to go. Proactive protection is possible with composites. So by using this adhesion zone technology where you don't have to remove that existing potentially hazardous coating on your pipe type cables, we can reinforce larger sections of cables. We can do it economically, we can do it fairly quickly. So all of a sudden there is an alternate to reactive maintenance, proactive maintenance with composites. It provides a long-term and highly reliable solution. We have not had any issues with any of the feeder lines that we have reinforced. They've all withstood the test of time, even when they're in extremely challenging conditions like stray current or pipes on the side of bridges that have salt water running down them. So this is a reliable, a tried and true system for reinforcing pipe type cables. So I appreciate your time. We're going to go through and take a few questions from the audience. By all means, if you have any additional questions, you can reach out to Advanced FRP afterwards or to me directly and ask questions. And I'd love to talk to you further about any of the specific systems that you may have where that could benefit from this technology.
Great, Rusty. Sounds like we've had a few questions throughout the presentation, so I'll share with you one of them. Maya asked, is there a reason why externally welded barrels are not reliably providing a 20-year service life?
Sure, thank you for that question. We've seen a lot of stuff in the field. A lot of utilities do things differently, but one of the reasons that I've personally encountered for externally welded barrels not performing as long as they're expected to perform was just a simple surface preparation. So the utility sent welders in, and they welded. They did a great job of welding the external barrel, yet putting on that corrosion barrier, um, the surface preparation wasn't done properly. So grit blasting is crucial for a lot of these corrosion barriers to provide that longevity. That was one major issue. The other major issue we've seen in the field is tying into the existing corrosion barrier and not creating a spot of potential corrosion right where those two tie in. A lot of existing feeder lines have very old coating systems. So you really have to test and ensure that a proper overlap is created when interfacing with the existing cathodic or existing corrosion barrier.
Great. Have another question here from Charles. His question is, do you see any ampacity loss when doing large scale pipe repairs with composites?
Yeah, that's a great question. We and our first utility partner were worried about ampacity loss. As I alluded to in the presentation, the ability of the pipe type cables to radiate heat into the surroundings is crucial. So we did a heat transfer study, and like I said, we've done over 12,000 linear feet of cable in the field. So in both cases, the heat transfer study showed that any ampacity loss would be easily contained in the over design of the system, and our customers have not reported any ampacity loss, even with large-scale composite reinforcement in the field. So to answer your question, no, we haven't seen any ampacity loss.
Great. Looks like those are the only questions we've had so far.
Excellent. Thank you, Carlos. So if anyone has any further questions, feel free to reach out to me. You can check out our website at www.advancedfrpsystems.com. There's a lot more information there. Or we'll follow up with an email with this presentation. And like I said, just reply and ask any questions you may have. Thank you again for your time, and I hope everyone has a great afternoon.